So now let's talk about electric field. So consider this small square in the region where there's an electric field. And this small square has an area vector, call it delta A, pointing in that direction. And this small square has a flux through it. And what we mean by flux is we say it has some flux phi sub E, which is E dot delta A. Well, this small little square could be part of a larger surface. And let's call this surface S. And so then the total flux through this surface S is then just the sum of all of the little bits of flux through all the little bits of squares. Well, we can make that a bit more precise in terms of an integral. So we have an integral over the surface of E, the electric field, dot dA, the differential area. And so this is some kind of surface integral. Well, how do we evaluate a surface integral like this? An integral over a surface of E dot dA? Well, in general, there's two cases that we need to concern ourselves with, and mostly we only have to look at these two cases. So in one case, we have an electric field, say, pointing this direction at the surface that we're interested in, and then the area vector will point perpendicular to the surface, always. And as you can see, in this case, the area vector and the electric field are always perpendicular to each other on this surface. So that's one case, when E and A are perpendicular. Then you have E dot dA just equal to 0. Another case is when the electric field points perpendicular itself to the surface. Well, that's also the same direction that the area vector points at each of the points on the surface. These are some samples. And so the electric field and the area vector are then parallel in this case. And so we have E dot dA, or rather the integral of E dot dA, is then just the electric field times the area of that surface. So let's look at an example. And so let's look at the flux of a point charge. So let's put a point charge at the origin here. Call it charge Q. And let's choose a surface, in this case just a nice one, a spherical surface with a radius r. So here's our surface around our charge, radius r. Okay, well, one of the first things we need to do is find dA, a little bit of the differential area vector. And so the differential area vector dA, well, it certainly points radially outward all over the surface of the sphere. And so dA is just dA magnitude times r hat. Okay, so it's obvious that we should use spherical coordinates in this case. And so then we can write dA as dl in the phi direction and dl in the theta direction, or r squared sine theta d theta d phi, and it still points in the r hat direction. Okay, so if you recall then for a point charge, the electric field E is 1 over 4 pi epsilon naught q over r squared r hat. So now we can calculate the flux of the electric field through this surface. And the flux through this sphere of radius r is, well, let's just call that phi sub E. And that's equal to the closed surface integral over the sphere of E dot dA. And well, that's a double integral of 1 over 4 pi epsilon naught q over big R squared r hat. Notice that wherever we had little r, we set big R, because we're at the surface. R squared sine theta d phi r hat. Okay, the r squareds cancel. Notice the limits on the integral for the theta integral, it's 0 to pi. The phi integral is 0 to 2 pi. And so the q over 4 pi epsilon naught we can pull out. And then we have two integrals here. And we're left over with sine theta d phi. And there's an r hat dot r hat, but that's just 1 by definition. So we have q over 4 pi epsilon naught, the integral over phi, and then the integral over theta. And those two integrals give us a factor of 4 pi, so we're left over with q over epsilon naught. So altogether, we find that the total flux through this surface, E dot dA, is equal to q over epsilon naught. And this is what we call Gauss's law. It's a very useful relationship between the flux and the charge. In words, what this means is that the flux through a closed surface is equal to the charge enclosed in that surface divided by epsilon naught. This epsilon naught is just kind of a conversion factor in some sense. More generally, we can write Gauss's law for not just one point charge, but for many, or for any other charge distribution, as the flux through the surface, or the closed integral of E dot dA, is equal to Q enclosed over epsilon naught, where Q enclosed is the enclosed charge of the surface that we have.